Hello everyone. So after having completed redox chemistry, we are going to start our next chapter, acids and bases, or the chemistry of acids and bases. Here we start from different theories of acids and bases. The very first theory is the Arrhenius theory, where the concept of acidity and basicity is explained. This is the primitive theory of acidity and basicity. So according to the Arrhenius theory, acids and bases are defined as the species which can release proton and hydroxide ion respectively. So what is written here? According to Arrhenius, acids are defined as the hydrogen containing compound which gives hydrogen ions in aqueous solution. So simple, which can release H plus ion is an acid. A base is simply defined as any compound which gives hydroxyl ion in aqueous solution. So this is also simple. The species which can release OH minus ion will be treated as a base. Now, the extension of the Arrhenius theory is the Franklin concept of acidity and basicity, which is the solvent system concept. According to this concept, or according to this solvent system theory, it depends exclusively upon the solvent of the species where it is dissolved. Solvents can undergo self-ionization and it produces a cation as well as an anion. So if the species produces the similar cation, then it will be treated as the acid, or if the species is producing the similar ion as the negative ion produced by the solvent, then it will be treated as a base. So an acid is a substance which by dissolution in the solvent forms the same cation. Look at here. Same cation as does the solvent due to self-ionization. We'll go through the examples below. Before that, a base is one that gives the same anion on dissolution which is produced by the solvent due to self-ionization. So what I have said here, suppose this is the aqueous medium. So on self-ionization of water, it is producing H3O plus hydroxonium ion and hydroxide ion. Ammonia on self-ionization produces ammonium ion and amide ion. On the other hand, sulfur dioxide on self-ionization produces sulfonium ion and sulfite ion. Now, what are acting as acids or bases in these mediums? Such as in aqueous medium, hydrochloric acid HCl will be treated as an acid because it can produce H plus ion or H3O plus ion, same as this one. On the other hand, NaOH will be treated as a base because it is producing this OH minus ion which is being produced by the self-ionization of water. In the next example, ammonium chloride. Ammonium chloride is generally known as a salt, but here, according to the Franklin concept, it will be treated as an acid because it can produce ammonium ion, and if the solvent is liquid ammonia, then it is producing the similar cation produced by self-ionization of ammonia. So it will be treated as an acid. In case of sodium amide or sodamide, it produces NH2 minus or amide ion, which is similar to the amide produced by self-ionization of liquid ammonia. So it is now a base, not a salt in liquid ammonia solvent. Similarly, sulfonyl bromide or sulfonyl chloride is an acid because it produces the similar cation SO2 plus this SO2 plus sulfonyl ion, or potassium sulfite, which we generally call a salt, will be called a base in the liquid sulfur dioxide medium because it is producing the sulfite ion SULPHITE sulfite ion similarly produced by self-ionization of liquid sulfur dioxide. So this is all about the Franklin concept, which is exclusively dependent upon solvent, but we have some limitations on these two concepts. What are the limitations? You can guess the limitations because Arrhenius concepts is completely confined on production of H plus or OH minus ions. So we cannot extend our theory on other substances such as oxides or similar things. Franklin theory, it is exclusively dependent upon the solvents. So we cannot also extend our concept on the suppose oxides or similar things, or other organic substances where no solvent interaction is involved. So the Arrhenius concept is limited up to only hydrogenated and hydroxylated compounds. That means this concept is limited to those substances which can produce only H plus and OH minus ions. Beyond them, their acidity or basicity cannot be explained, such as Lewis acid. Okay, BCl3, this is the Lewis acid. Can that be explained by these two theories? No. HCl cannot be regarded as an acid in benzene medium. On the other hand, HCl is a very good mineral acid, but in presence of benzene it cannot produce H plus ion, so it is not an acid. Similarly, metal oxides, as I have been saying about them, metal oxides are not regarded as bases. In the solvent concept, the Franklin theory does not consider a number of acid-base reactions included in Protonic definition. It limits acid-base phenomena to solvent systems only. Thus, it does not explain the acid-base reactions which may occur in the absence of solvent. That means, if there is no solvent, our acidity or basicity cannot be explained. It cannot explain the neutralization reactions occurring within the presence of the ions. Thus, this theory can simply be said to be an extension of the Arrhenius water-ion concept or water-ion system. As I have said, the Franklin theory is the extension of the Arrhenius theory. So, we move on to some such a theory which is much more reliable than these two, or which can explain more compounds on the basis of their acidity or basicity, and this concept is the Bronsted-Lowry Protonic concept. Here, a substance which in presence of water or in absence of water, if it can produce proton, it may not have proton itself, like Arrhenius acids. In presence of water, if it can produce H plus ion, then it is an acid, or it can accept a proton, then it is a base. So here two things are involved, two acids and two bases are involved. If some species accepting a proton, it becomes a base. If some species are releasing a proton or producing a proton, it becomes a base. Okay, so two acids and two bases are involved. So what are the salient features of the Bronsted-Lowry Protonic concepts? Acids are defined as proton donors and bases are proton acceptors. So acids can produce proton or they can donate proton, and bases can accept proton. This concept makes acid-base reactions independent of solvent. So we are going beyond the limitations of the Franklin concept, where solvents are exclusively involved, but here no need of a solvent. A proton can be accepted in absence of water also. So this concept makes acid-base reactions independent of solvent. Now this point is colored in red. This is the most important point. When an acid releases a proton, the residue must be a base, and this base is known as the conjugate base. Suppose HCl releasing the H plus ion, so the residue is Cl minus ion. Now Cl minus ion is treated as a base. So the acid 1 becomes the base 1. On the other hand, if when a base takes up a proton, then it gives its conjugated acid. Suppose NH3 is a base, so it takes a proton H plus, so it produces NH4 plus, so it becomes an acid. So NH3 is a base. On the other hand, NH3 plus is an acid. So this point is most important. So acid 1 plus base 2 equal to base 1 plus acid 2. This is the salient feature of the Bronsted-Lowry concept. Therefore, an acid-base reaction involves two acids and two bases. That is, this is the explanation of this point. Now we move on to some examples. What are the examples? Example number 1. HCl plus H2O. HCl accepting a proton. Okay. I'm sorry. HCl releasing a proton to become Cl minus. So 1 is 1 here. Here is 1 and here is 1. HCl becomes Cl minus. Now species 2 is H2O. Now this species 2 has become H3O plus. So acid 1 plus base 2 equal to acid 2 plus base 1. Here the conjugate base of HCl is chloride ion. On the other hand, the conjugate acid of H2O is the hydroxonium ion, that means H3O plus. In the reverse, for the reverse reaction, if H3O plus is the acid, then the conjugate base of this acid is water, and if Cl minus is the base, then the conjugate acid of this Cl minus ion is HCl. Next, ammonium ion is an acid. When it reacts with water, which is behaving as a base, then it produces acid 2 H3O plus and base 1 ammonia. That means the conjugate base of ammonium ion is NH3 and the conjugate acid of H2O is H3O plus. In all the examples, the conjugate acids of H2O plus is H3O plus. So H2O in all these examples, all the 4 examples are behaving as bases, and in every case their conjugate acids are H3O positive. Now the species like HCl, ammonium, sulfuric acid or bisulfate ion, all of them have the corresponding conjugate bases such as chloride, ammonia, bisulfate and sulfate. So we find that the ions HSO4 is an amphiprotic ion. Amphiprotic means it can receive proton as well as it can release proton. When it is receiving a proton like here, so it is a base. On the other hand, here in example number 4, it is releasing proton, so it is the acid. So it is both behaving as acid as well as base. So in example number 3 and 4, HSO4 ion may behave both an acid or base. Similar type of examples are bicarbonate ion, dihydrogen phosphate ion, hydrogen phosphate ion or biphosphate ion, and the bisulfide ion. What are their conjugate acids and what are their conjugate bases? Try to imagine the conjugate acids of these ions should be, for HCO3 the conjugate acid should be carbonic acid, that means H2CO3. For this one should be phosphoric acid, that means H3PO4. For this one, the previous one is the conjugate acid, that means the H2PO4 minus negative ion is the conjugate acid. On the other hand, the bisulfide ion has the conjugate acid hydrogen sulfide gas. Look, the conjugate acids are respectively H2CO3, H3PO4, H2PO4 minus and H2S. And these species are amphiprotic, as I have said. So after having released the proton, that means when they are behaving as an acid, then they can produce their conjugate bases. So what are their conjugate bases? The corresponding conjugate bases are the carbonate ion, the hydrogen phosphate ion, the phosphate ion or the sulfide ion. Now we move on to example number 5, 6 and 7. Now here we find that HS minus, the bisulfide ion. So give an example of a species which contain bisulfide ion. Suppose sodium bisulfide, NaH. I'm sorry. This is sodium bisulfide, NaHS. So when sodium bisulfide dissolved in water, it produces hydrogen sulfide gas. Why? That is a question. Or it is behaving as a base, the HS minus. Why? The answer all belongs to this equation. You write this equation and give the explanation that when it reacts with water, it reacts as a base, while water is playing the role of an acid. So water is playing the role of an acid, so it is producing OH minus ion after having released the proton. On the other hand, that proton is being received by HS minus ion to produce H2S. So it is playing the role of a base. And since H2S gas is produced, so sodium bisulfide, when dissolved in water, it produces the smell of H2S gas. And in another example, here acetic acid is an acid, but it can act as a base. This is the most important advantage of this theory, that an acid can also become a base. In the next examples, you will find that nitric acid can behave as a base, sulfuric acid can behave as a base. So depending, it is their comparison. That means comparison between two species, which one is the stronger acid. So in presence of HCl, acetic acid can act as a base. Its conjugate acid, what is the, if it is a base, then what is its conjugate acid? Its conjugate acid is CH3COOH2 plus ion. And on the other hand, HCl has the conjugate base Cl minus. Now Cl minus is a base, so when it is playing the role of a base, then what is its conjugate acid? Its conjugate acid is HCl. Okay. So in the reaction number 6 occurs only in the pure acetic acid medium, where acetic acid plays the role of a base. In example number 8, 9 and 10, what happens? You find here perchloric acid is a stronger acid than sulfuric acid, so sulfuric acid is a base here. And what is the conjugate base of sulfuric acid? It is H3SO4 plus ion. Hydrofluoric acid is a very powerful acid. It can penetrate through glass. You know, you have read earlier in your lower classes that hydrofluoric acid is a very dangerous acid. When you put it on a glass, it produces a hole. So HF even can become a base in presence of perchloric acid. Actually, perchloric acid universally is the strongest acid. No more acid in this universe can be stronger than perchloric acid. That means it has the highest capability to produce proton. Now, in presence of perchloric acid, HF plays the role of a base, and what is its conjugate acid? Its conjugate acid is H2A plus. So species 2, that is why base 2, acid 2. This is species 1 and its corresponding species 1 is this one. So acid 1 is producing base 1. That means the one species is acid here and its conjugate base is 1 here. Okay. There was one more example left, that is nitric acid, which is also a very strong acid, but in presence of hydrofluoric acid. So we can make a sequence: perchloric acid greater than hydrofluoric acid greater than nitric acid. Okay. Next example 11 and 12. Urea is, when reacts with ammonia, it is an acid. When urea reacts with formic acid, it is a base. So look out at their conjugate acids and conjugate bases. We move on to example number 13. In this reaction, from this reaction, you will be given a question that when hydrogen is passed through molten potassium deuteroxide, then HD gas is coming out, while the hydride ion is not detected. So what is the answer of this question? I repeat the question. While passing hydrogen through molten potassium deuteroxide, then hydride ion cannot be detected, but the hydrogen enriched with deuterium is coming out. Explain why. So the answer is these two reactions. This is the forward reaction and this is another reaction. This is not the backward reaction, this is the another reaction. So what is the forward reaction? Hydrogen H2 plays the role of an acid here, which reacts with the deuteroxide ion to produce DOH and hydride ion. These hydride ion do not remain in the solution. It further reacts with DOH to produce HD and OH minus. That means this OD in the reverse reaction has been substituted by OH minus ion. On the other hand, instead of H2, it produces HD. So that is the answer. Now we move on to example number 14 and 15, where toluene reacts with CH3Na and this hexaquoferrum 3 ion reacts with H2O. So can you imagine what should be the conjugate acid and conjugate base? This is species 2, what should be here? And this is species 1, what should be here? Or this is species 1, what should be here? And this is species 2, what should be here? Okay, try to imagine or try to guess the answers. The answer should be, this is, if this is a base, then it takes up 1 proton. According to the Bronsted-Lowry theory, it can receive a proton because this is a base, and this can release a proton. So if this can release a proton, so this will become CH2 negative ion, and this, after having received the proton, it will become methane gas, and that sodium plus ion will be here. So the answer is this one. It's producing methane gas with C6H5CH2 negative and Na positive, and this hexaquoferrum 3 ion produces this species where 1 OH minus ion gets into the ring and 1 positive charge is reduced. So this is the corresponding conjugate base of this species 1 acid. Okay, so the reaction number 14 takes place in hydrocarbon solvents. Both methane and toluene are weakly acidic, but toluene is more acidic than methane. So what are the salient features of this Protonic concept? That water, liquid ammonia, anhydrous hydrofluoric acid and acetic acid are the amphiprotic solvents. As I have said, that they can receive proton as well as this can release proton. So they can both accept and release protons and act both as acid and base. It includes a large variety. That is the main advantage of this theory. It can cover a large variety of substances in the realms of acids and bases. Relative strengths of acids and bases can also be expressed according to this theory in the same manner as in the Arrhenius definition. Okay, this will be explained later. On the next slide, I'll explain how it relates to the Arrhenius definition. The procedure may also be applied to other media to determine the relative acid-base strengths of the substance. As you have seen in the previous examples, that we have a sequence of relative strengths of acidity, such as perchloric acid stronger than hydrofluoric acid, stronger than nitric acid. And finally, the hydrolysis of salts and catalytic activity of acids may also be explained in the light of this theory. Now, this point to be explained this way, that if this is the reaction H plus H2 equal to H3O positive plus A negative, then this is the equilibrium constant and this is the acid dissociation constant. Now, in the Arrhenius theory, the acid dissociation constant should be this one A minus, this one H3O positive and this one HA only. So, take this active mass of water to the left hand side. This is another constant because the concentration of water is almost same. So, it is another constant K dash. So, this is actually Ka of the Arrhenius theory. So, that's this way it can relate the Arrhenius theory. So, now some limitations of this theory are also there, because from the very beginning I have saying that release the proton or receive the proton, release the proton or receive the proton. So, this is the disadvantage, only proton is involved and no other species can be involved. So, some Lewis acids, acidity and basicity cannot be explained in this light of this Protonic concept. So, it puts sole emphasis on the proton in determining acid-based criterion. It fails to include substances which do not contain any proton and exhibit acid character in certain reactions, for example, aluminium chloride, this is the Lewis acid, boron trifluoride or SO3, etc. So, that's all for about the three concepts of acids and bases. We shall discuss the other theories in our next class. So, that's all for today. Thank you.